So we'll pick up today with example 4, and we kind of mentioned this idea on Friday, the difference between verifying something is true and proving that something is true. Anybody want to take a guess without reading what the difference is? Tyler, better than raising your hand, you raise your whole body. Yes, go ahead.
Verification, I guess, is like a statement saying something is proof is actually showing the evidence.
Good try. Yes.
Verifying is using specific values.
Uh-huh.
Proving is using like X and Y.
Variables. Yeah. They're both statements. If you verify that something's true, you're only showing that it's true in that specific case. For example, it is not raining outside this window. I just verified it right now. It is also not raining outside this window right now either. Or right now. Okay? Does that mean it's not raining outside any window right now? No, I've only verified it for one window. Dallin, can you check that window? Is it raining outside that window right now? No. So, if it's not raining outside of two windows, it must not be raining outside any windows, right? Wrong. Good. You could check thousands and thousands of windows out of which it would not be raining, but then you could not, with any assurance, say then, therefore, it's not raining outside of any windows. Because it could be raining outside of just that one window. And if we haven't checked it, we can't say that it's not raining. By the way, we're supposed to get like 4 inches of rain tonight. So if you look at your window tonight, you'll probably see rain. Okay. So verification in specific cases, and proof is showing it's true in all cases. And the way that we could do that here in this case is to verify using actual numbers and to prove using variables, which then can be any number could then take the place of those variables. So here's kind of what I was just saying. No amount of verification constitutes a mathematical proof. If you check something and it's true for like the first 5 billion cases, you can't say it's true in all cases because there could be that one little case where it's not true. And in mathematics, if it's not true for all cases, we say it's not true. It's false, even though it might be true for most of the time. So here's example 4. We're going to verify, before we get into full-fledged proof, that this identity is true, and I chose a couple of angles here. So this might be something you have to do on your test on Thursday, on the free response. I'll say verify. So what you're going to do is you're going to do the same thing that we would normally do for a proof. You're going to draw a line down the equal side, which keeps you from cross-contaminating. But now instead of getting one side to look like the other, you're going to pick a value. And let's choose pi 6. So you're going to tell me which value you're going to use, and I might have you come up with your own values. In this case, I gave it to you. I would probably recommend using unit circle angles, right? So here's what we do. We just plug it into the left, and we plug it into the right. And very similar to a proof now, you just work on each side independently until the bottom lines are the same. So what is tangent of pi 6? Square root of 3? Or square root of 3 over 3? Well, the ordered pair at pi 6 is square root of 3 halves, 1 half. And it's y over x, so it's 1 over the square root of 3. So it should be square root of 3 thirds. Okay, now over here on the right side, before I can take the cotangent, I have to simplify inside. So what is pi halves minus pi 6? Pi halves is how many pi 6? 3, right? So 3 pi 6 minus 1 pi 6 is 2 pi 6 or 1 pi thirds. So much like a proof, the process is really your product. So, no, you don't have to. You don't have to. But again, when in doubt, do not leave it out. Because as I was saying, the process is the product. But we can make that leap with you. Pi halves minus pi 6 is pi thirds. And what is cotangent of pi thirds? The ordered pair is 1 half square root of 3 halves, so it's x over y, which is square root of 3 over 3. Now, this one is not as exciting as a proof, so at the bottom here, we don't, like, celebrate as elaborately. We don't say, like, sizzle or, you know, heck yes. We maybe just put a check, right? It's like, okay, this happens to work for pi 6. Big deal. And by the way, it's still not raining outside this window. Now, I'm not going to do it for 7 pi 4ths, but it would be done very similarly. And it does work. It does work, okay? Counterexample. What is a counterexample? Well, here is one example of a counterexample. This is, I think, it's not for Mica brand countertop surfacing. I think it's probably Wilson Art brand. But there's an example of a counterexample, and that's not what we're talking about here. Hello, Savannah. What is a counterexample? Counter means against, right? Exactly. You may know people that are really good at counterexamples, right? They're called wet blankets. They spoil fun. They're naysayers, right? You're always having a good day, and they're like, well, actually, like, get out of here, right? Mathematically, that's what a counterexample is. It's the, well, actually, kind of thing, right? You're like, hey, this thing is always true. Well, actually, you know. So it only takes one example to show something is false. Like I said earlier, it can be true for a billion cases and only false once. And in mathematics, we would say then it's false. So sometimes it's easier to disprove something than it is to prove something. And a counterexample then would be the example that shows that something is not true, okay? The well actually part. So here's example 5. Find a counterexample to disprove each of the following quote-unquote identities. We talked about the use of quotations last week. If I put quotation around identities like free meat, what does that mean? They're probably really not identities, right? Right? Yeah. So, we talked about this at the beginning of the year. We spent a lot of time going over these common mistakes. The square root of x squared plus y squared, some people still might think it's x plus y. Is it? No. So let's come up with a counterexample. Let's say when x equals 0 and y equals 1. We're going to define what our variables are. All right, so let's see. If I do the same thing, I plug it in on the left, I get the square root of 0 squared plus 1 squared. That's going to be the square root of 0 plus 1. That's the square root of 1, which is 1. And if it's not true, it shouldn't be the same on this side. Well, let's see. That's 0 plus 1, which is 1. Hey! I thought you told me that it wasn't true. I just proved that it is. I verified that it's true when x is 0 and y is 1. What now? Try another one. Right. If something is false, it may be true for a kabillion zillion cases, but if it's false, you have to find an example that shows it's false. If you happen to pick one that shows it's true, you have not found a counterexample. Now, y'all are going to have the luxury of knowing beforehand when you go in if something's true or false, right? In general, that's not how it works, right? In general, you're going to have to determine if something's true or false. And if you just tried one and you got lucky and you walked away, you're not being very thorough. So this is not a counterexample. There are several values for which this is true, not just 0 and 1. So let's pick some other examples. Like you said 5 earlier, Joseph. And let's try y equaling what? -5. Okay, good. So we define what they are on the left, and now we plug in, and we get 5 squared plus -5 squared. And that's going to be the square root of 25 plus 25. That's the square root of 50, which simplifies to what? 5 square root of 2. Good. And on the other side, we plug in, we get 5 plus -5. That's 5 minus 5. That's 0. Does 0 equal 5 square root of 2? No. So, because it doesn't work every time, we say it doesn't work. So when can you replace the square root of x squared plus y squared with just x plus y? When can you just replace the square root of x squared plus y squared with just x plus y? Never. Unless you're on a game show and you're trying to lose. I don't know. Why would you never want to call the square root of x squared plus y squared x plus y? Because it's not equal to x plus y. We just proved it, okay? We've proved that it's not equal. One counterexample is all it takes to prove something's not true. Well, actually, did you think about x equals 5 and negative 5? Maybe that's actually a good friend to have, right? They keep you from making careless mistakes. Here's one later on that I guarantee at least one of you is going to think is true, even though we're going to prove right now it's not true. Sine of x plus y is equal to sine of x plus sine of y. Not true. What do x and y represent here? Angles or ratios? Angles. So if you take the sine of the sum of two angles, it is not equal to, apparently, the sum of the sine of the two angles. It is equal to something, and we're going to learn that later on. But it's not sine of x plus sine of y. In other words, you cannot distribute the sine into its own angle any more than you could do that with logs. Remember with logs, you couldn't distribute the log? In general, you can't distribute a function inside itself. So let's come up with some examples here. Let's let x equal 0, and let's let y equal, what, pi halves? How does that sound? So on this side, I get sine of 0 plus pi halves. And that's the same as sine of pi halves, which of course is 1. And on this side, I'll get sine of 0 plus sine of pi halves. What's sine of 0? 0. What's sine of pi halves? 1. What's 0 plus 1? 1. Proof must be true. It's raining outside this window, so it's raining everywhere outside of every window. Wrong. See, that would be the claim. And you don't want to do that. That's silly. So if you happen to choose one that it works, you chose wrong. Or just choose again. Any other ideas? Pi 6 and pi 6? Sure, might as well. Let's try it. Pi 6 equals x, which equals y. So we're going to get sine of pi 6 plus pi 6 on this side. They could be the same. There's nothing wrong with that. That would be the sine of 2 pi 6 or 1 pi thirds. What's sine of 1 pi thirds? Square root of 3 over 2. And over here, if we plug in sine of pi 6 plus sine of pi 6, that's a half plus a half. And two halves make a whole. Crawl through the hole and you're out. Well, those don't equal each other. So there you go. It's not true. Counterexample. You're basically proving something's not true. And all it takes is one, just one, and you've accomplished your goal of disproving something. And I'm not going to do this one, but does cosine x plus sine of x equal 1? It only would equal 1 if cosine and sine were both what? Squared. Then we have Papa Pig. Okay? So you can't just take the square root of cosine squared plus sine squared and call it cosine plus sine. We just prove that over here in part A that does not work. So they have to be squared. Okay, now example 6, this is where it starts getting real fun. This will be similar to possibly your free response on your test on Thursday. Simplify the following trig expressions to a power of a single trig function. To a power of a single trig function. So there'll be some trig function raised to some power of x. So like sine squared of x, cosine cubed of x, something like that. So we kind of have a target, but not really. We don't know what the trig function will end up being, nor do we know what the power will end up being. All right, so this is kind of like preliminary proofs. We're starting with an expression, and we're trying to manipulate it. So with expressions, it has to be equivalent the whole time, right? So you can add a clever form of 0. You can multiply by a clever form of 1. You can factor. You can combine like terms. You can divide out common factors. Or you can make replacements of one expression with an identity, something it's equivalent to. So, any ideas what we could do to start here? We have two terms. I want to eventually get it down to a single term that is a single trig function raised to some power. Well, we can only combine like terms. So in the first term I have a sine cubed, in the second term I have a sine and a cosine squared. Those aren't like terms. What to do? What can we do? I just said we could do a couple of things. We can place something with an identity. Do we have a sine cubed identity? No. We have a sine identity. We can call sine 1 over cosecant. You want to get cosecant involved? Well, you could replace the factor sine of x with 1 over cosecant, yeah. But then we're going to have sine and cosecant and cosine. And we're trying to get into a single trig function. I'd be working backwards. I would introduce a third. Could I say what? Cosine of? Oh, good. Let's look at that. I could use the cofunction identity. And I'm just going to be thinking out loud here. I'll be writing it down, though. I could call that cosine of pi halves minus x, right? I could make that replacement. Here's the only problem with that. The only way I can eventually get two terms into one is to combine like terms. And to be like terms, the angles have to be the same. So then I would be left with still two angles of x, and now I'd have an angle of pi halves minus x. So doing that is not illegal, but it changes the angles. And the angles, help me, angels. They have to match. The angles have to match. What else? Man, it'd be nice if they were all already in terms of either sine or cosine. Wouldn't that be great? Yes. Distribute the sign. Factor out the sign. Okay. Now we're talking about something that might be effective. We have two terms. They each have a factor of sine of x. So let us try it. We don't know if it's going to work, but you have to kind of try something here and see if it works. And if it doesn't, you learn why from your mistake. And then you back up and you try something else. So if we factor out a sine, we're left with sine squared plus cosine squared. What? Oh, there's a 1 right there. Sure. 1 times cosine. Yeah. And if you redistribute, and it's always a good idea to check, what's sine of x times sine squared? Sine cubed. Plus, what's sine times cosine squared? Sine times cosine squared. Great, so we factored it out. Now what? Who's slapping you in the face? Papa Pid, right? Papa Pid is slapping you in the face. I'm like, stop it, Papa Pid. I'm trying to work this problem here. And, of course, if you don't know who Papa Pid is, you think someone's just slapping you in the face. And that's why you have to memorize your identities, because you have to know them when you see them, and you also have to think about them before you see them so that you can maybe replace something. What is sine squared plus cosine squared? It's 1. It's Papa Pid. So it becomes sine of x times 1, and, of course, anything times 1 is itself. Did we get it down to a power of a single trig function? We did. Sine of x to the first. Wow. So it all started with overcoming the inertia of just staring at it. Sometimes you just have to do something. In this case, factoring out sine worked. Is that the only way you could have proceeded? Heck no. Okay? You could have also done it this way. You could have said, you know what? I have a sine cubed, a sine, and a cosine squared. I'm going to put it all in terms of sine, because 2 of the 3 are already sine. So I'm going to put parentheses around cosine squared, and I'm going to use Papa Pid to put that in terms of sine. And here's where knowing the identities help. You know that you can relate cosine squared to sine squared a la Papa Pid. So if cosine squared plus sine squared is equal to 1, then cosine squared is equal to 1 minus sine squared. Remember, you can manipulate the identities. So that would be another way you could have started. And now you're like, cool, everything's at least in terms of sine. And now you can do any obvious math, which would be to do what? Now we can distribute. And that would give you sine cubed plus sine of x times 1 is sine of x minus what sine times sine squared? Sine cubed. And what's sine cubed minus sine cubed? 0 plus sine is sine. Which way was more correct? Either was more correct. Now, the first one was more efficient, so maybe that's what you strive for. Because if you could be efficient, you're conserving energy, you're conserving paper, which means you have more energy, more space for more math problems. It's a win-win. All right, cool. Letter B. Letter B. Perfect. Secant of x minus 1 times secant of x plus 1. I want to end up with a single power of a single trig function. What to do, what to do. Oh, right. You can relate secant squared to tangent squared, but they do have to be squared. So you can't. But yeah, if it were secant squared minus 1, you could certainly call that tangent squared. Very good. But it only works if they're squared. Can you just square it? Is that legal? Can you just square something? No. We don't have an equation, so we can't square both sides. And if we did, that's not how you would square both sides. So when you square something in general, you change its value. These are expressions. There is something we could do, right? When in doubt, just do some obvious math, right? Over here, we started on the second version with the trig replacement, and then there was some obvious math to do, namely distributing. The first version, the obvious math was to undistribute or factor. So you could distribute. Now, these are special factors. What do you call them? Something plus 1, something minus 1. Those are what you get? Very good. They're conjugates. They're conjugates. And whenever you multiply two conjugates, you always get a difference of two perfect circles. Squares. Good. So let's see. You got secant times secant. That's secant squared. And then you're going to get minus secant on the inside plus secant on the outside. They cancel. And you're left with minus 1. No, that's not cosine squared. But if 1 plus tangent squared of x is equal to secant squared of x, then remember, you can bring the 1 across, and secant squared minus 1 is equal to tangent squared of x. So again, once you have the identities memorized, you can manipulate them algebraically. So you could just say secant squared minus 1 is in fact tangent squared. Or, if you didn't want to solve the identity for secant squared minus 1, you can replace secant squared with what? 1 plus tangent squared, right? That is just flat out using the actual identity. And of course, it's just one extra step. What happens with your 1s? They cancel. And there you go. So really all we're doing is some algebraic things, factoring, expanding, and using trigonometric substitutions with identities. So there you go. If you don't have the identities memorized, you have no idea what your options are, and you're going to fail. You will fail. So you got to memorize the identities. And you have to be familiar enough with them that you know what your options are. Like you have to realize, oh, I can relate secant squared to tangent squared. Oh, I can relate cosecant squared to cotangent squared. Or I can relate cosecant squared to sine squared, a la reciprocal identity. So it's more than just flat out memorizing them. You have to know them fluidly enough that you can refer to them. All right, letter C. Oof. Okay, this one looks great. The first thing that you might notice is that there's lots of stuff. And we eventually have to get this down to a single power of a single trig function. Well, maybe the first thing to concentrate on is the negative angle. Because all of the other angles are just plain old theta. There we have a negative theta. And as we already mentioned, all the angles have to be the same if we are eventually going to combine them. So what identity can we use to take care of a negative angle? The even-odd identity is good. Is secant even or odd? Even. So what can we do with the theta? Bring it out front or just get rid of it? Just get rid of it, okay? So that's secant of theta. The other thing is you have two terms that are fractions, 1 over something. Man, it'd be great if they weren't fractions, wouldn't it? So do we have some identities that deal with 1 overs? Yeah, they're called the reciprocal identities. So maybe without even realizing if it's going to bear fruit, we just try it. 1 over cosine is the same as secant, so that's secant minus 1. And then this is cosine squared. Now plus secant of regular theta plus, what is 1 over cosecant squared? Sine squared of theta. So are we making progress? I'd like to think so. All of our angles are the same now, and we got rid of the fractions. Now do you want to go ahead and just multiply it out? Do you want to just FOIL it out? You could, but every time you do something, a little bit of obvious math, then look to see if you can combine like terms or do some kind of identity replacement. Cut it out, Papa Pig. Notice me. Notice me. That's all I'm asking. I'll quit slapping you in the face if you just notice me. Yeah. They don't have to be written side by side, do they? The associative property of addition. I have a cosine squared plus a sine squared. I can replace those two terms with a 1. Okay, so I'm left with secant of theta minus 1. And then the two purple terms become a 1, and I'm left with a plus secant of theta. They become a term, not a factor. Now what? The 1s divide out? What? Cancel. How? It's the same as the previous problem. Right. So if you want to, subtraction is not commutative, but addition sure is. Now it's the product of two conjugates. We just had this. This is the previous problem in disguise. That's secant squared of theta minus 1, which is tangent squared of theta. So believe it or not, we have just constructed an identity. B is equal to C if the angles were the same. One's x, one's theta. But that's an identity. They're equal to each other. Pretty nice. Pretty nifty. So inch by inch, it's a cinch. You just chip away at it. And as you work straight down, everything above and below have to be equivalent to each other. If you're only going to work on one little part, you got to rewrite the other part and work straight down. Kind of fun, huh? It's an adventure. It's an adventure. All right. Letter D. 1 minus sine squared over cosecant squared minus 1. Hey, do the 1s divide out? No, we can only divide out common factors. Those are terms. What to do, what to do. The numerator, 1 minus sine squared is equal to what? Cosine squared. Good. So you realize that because you have your PIDs memorized. Good. And then cosecant squared in 1. I think we could do a PID on that one as well. Whenever you have a squared trig function, plus or minus a 1, it's probably going to be some trig. Cotangent squared. That's cotangent squared of x. Oh my gosh. Look what happens. The c's divide out, the o's divide out, the 2's divide out, and the x's divide out, and we're left with s over t. Don't that cool? That doesn't work. What can we do now? Good question. Can we put it back in terms of x, y, and r? You can, but you don't want to. The only reason we did that in the beginning is because we were proving fundamental identities. So they were the basic building blocks of the other identities. There was no other way to prove them. Now, we're going to be using those identities themselves to prove things. So don't put it back in terms of x, y, and r. Very good. Yeah. One of the things that's helpful, and this is another strategy, if you ever get stuck, put everything in terms of sine and cosine. And we know from the unit circle that we can do that. because we can get all 6 trig functions just by knowing cosine and sine. So everything can be put in terms of sine and cosine. All right. So if you want to do that, cosine squared of x all over cotangent squared would be what? It was your idea. What would it be equal to? Good. Cosine squared over sine squared. Remember, the ratio identities and the reciprocals work for any power. So I just replaced cotangent squared with cosine squared over sine squared. Now you have a complex fraction, and you're always happy when you have a complex fraction, because the next step is always to eradicate the complex fraction. So at least you know what to do next, which is state change flip. Very good, Tyler. Cosine squared times sine squared of x over cosine squared of x. And if you want to put that first one over 1, now what happens with your cosine squareds? They divide out, and we're left with sine squared over 1, or just sine squared. And that's a single power of a single trig function. Yes? Yes. This step is totally required. If you went from here to here, I would count off this check. Because a lot of people, when they do that, they do it wrong. Okay, so it kind of goes back to what I was saying the other day in a proof. If there's like a mathematical reason for something, you need to show that step. And the reason there would be like division algorithm. Dividing by a fraction is the same as multiplying by a reciprocal. So yes, I do want to see that step. And it's for your own benefit, because it's to prevent you from making a careless mistake. Now, I will say that sine squared divided by 1, you don't have to rewrite it and say that and then it's equal to sine squared. We can infer that right there. But again, when in doubt, should I put that step or not put it? You should what? You should put it. Yeah. Okay, if you think you might lose points for not showing a step, show the step, because the process is the product. That's what we're grading. Otherwise, if we weren't grading the process, then you could just do this. You could just say that. And I'm like, good, awesome, well done, fantastic. That leaves a lot to the imagination, though, right? It's like, once upon a time, the end. Oh, great story. Great story. No, the story is in the plot. And that's what all this is. Oh, look at that salacious plot. The climax would be probably right here, huh? Oh, and then they divide out, and then it's the denouement. The falling action. All right, and then the end, right? Okay. Letter E for elephant. I'm going to let you do this one on your own. And I'm going to give you a minute to struggle with it, and then we'll come together. Get it to a single power of a single trig function. Struggle is part of the process, by the way. There's nothing wrong with struggling. The problem is if you give up. You have to work through the struggle. You got to try a different method. You got to learn from your mistakes. What works, what doesn't work. Discovering methods that don't work is actually success. Still not raining outside this window, but it's getting awfully close to raining outside this window. Alan, you keep working. I'm going to check the window over here. Still not raining outside the other window. So it must not be raining anywhere. Sometimes it's helpful to have an overall objective, right? If you don't know where you're going, any road will get you there. We're trying to eventually write this as a single power of a single trig function, which means we need to end with one term. How many terms do we have? 2. As I mentioned on Friday, if I want to get 2 terms into one term, and I have at least one fractional term, we're going to need a what? We're going to need a common denominator, aren't we? So you could do that. Now, maybe you're looking at sine over cosine, and you're going, ooh, 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 ooh. That's what? Ooh. That's tangent of x, and that's good if you recognize that without getting slapped in the face by tangent. That's good. But that would introduce a third trig function, wouldn't it? We already have sine and cosine. If you get tangent involved, So maybe what trumps that first move is to get a common denominator. So you could do your crisscross applesauce, right? But maybe we don't do that. Let's go ahead and on the next line we'll do this. Your common denominator is the product, 1 minus sine and cosine. So I'm going to multiply this one by cosine over cosine, and then minus sine of x over cosine x. It already has the cosine. It needs the 1 minus sine over 1 minus sine. See that? So all I did is I just took each of those two and multiplied by a clever form of what? 1. And is that allowed? Yeah, 1 is the identity element of multiplication. And now my common denominator is the product. So on the next line, I can just join them together already, and my common denominator is 1 minus sine times cosine. Now I'll multiply straight across. In the top, I get cosine times cosine, which is cosine squared. And then I'm going to distribute, but you got to be careful because it's minus. I'm actually going to distribute not a sign, but a negative sign. And let the negative be tied to the numerator. So a negative sign times the 1 is negative sine of x. And what's a negative sine of x times a negative sine of x? Positive sine squared of x. Okay? This negative right here can really derail you if you don't take it into consideration. All right? And now, without being backhanded across the face by the abusive Papa Pid, he can be, you just realize, okay, I see you, Papa Pid. Back off, man. We can call that what? Yeah, negative sine of x plus 1 or 1 minus sine of x, yeah? And on the bottom, I have my two factors, 1 minus sine of x and cosine of x. Now, when they're written side by side like this, at least the 1 minus sine of x has to be in parentheses, right? Otherwise, it looks like it's 1 minus sine times cosine. Now what? Something divides out. And we had this conversation earlier. If you're going to divide out your 1 minus sine of x's, that does not quite do the trick. What must you do in the numerator? You must put it in parentheses if you're going to show me the dividing out. If you're going to draw a line like that to show that it divides out, you need to group the entire quantity together. And now, what does that leave in the numerator when it divides out with itself? A 1. So really what we're left with is 1 over cosine of x, which is equal to secant. And there you go. Sweet. That's a single power, single trig function. So all of this step up here that we started with, it was really just secant in disguise. Right? So maybe if secant went to prom this year, it would go dressed as this. Because it is a masquerade prom. Who is that over there? I don't know. I don't recognize it. I'm secant! Oh, good one, secant. Good disguise. All right. Letter F. Again, I'm going to give you another minute on your own to at least maybe come up with some legitimate first move or an overall strategy or some prayer, okay, that you might recite. The weather report is still not raining outside this window. Should be a daily feature on the morning announcements, right? Weather report from Corpy's window. Not raining. Back to you. And then from that you can infer what the weather is everywhere, erroneously. You may be lost just trying to read that thing, huh? What's the variable in this problem? Beta, right? We're using beta to represent the angle. Don't forget your angle. As long as it's a variable, it can be anything. We don't have to just restrict ourselves to x's and y's and thetas. All right, two things that I would first notice is it's nice if all the angles are just straight up beta. I have a negative beta over there, so maybe I can use the even-odd identity to get rid of that one. And I have pi halves minus beta. I'd like for that to be in terms of beta. Do we have an identity for that? Cofunction identity. Good. So first step, and this kind of trumps everything, is to try and get your angles the same. Always try to get your angles the same. Did you hear that? Your first task, if your angles are different, is to try to get them to be the same. So in the top, negative tangent of pi halves minus beta is now equal to negative cotangent of beta. Okay? And then cosecant of negative beta is the same as what? Negative cosecant of beta. Now, if you write it like that, I'll probably take a check from you. Because when you put dot negative, it sure looks a whole heck of a lot like what? Subtraction instead of multiplication. So I am not a fan of dot negative. I don't like it. Okay? So if you're going to do that, put extra parentheses. Or you could bring the negative factor out front if you want and put a positive sign. I'll do that on the next line. And then cotangent squared of beta plus 1. Right now, maybe you're not realizing if you should do anything with it or not, so you leave it. And that's another thing that you have to learn through trial and error. Sometimes you do a little bit of work in the top and you could do work in the bottom. But sometimes if you replace too many things at one time, then the two things that you need to connect, they're gonna pass each other. Okay? So if you're not sure what to do in the denominator, maybe because now we have a cotangent in the top, maybe you leave it like that. You just kind of chip away at it. So at least in the numerator now, a negative times a negative is a positive. So I know it's cotangent of beta times cosecant of beta. And would one of those cotangents then divide out with one of the cotangents in the bottom? No, because why? Well, if it was just cotangent over cotangent squared, one of them would divide out. But the plus 1 in the bottom ruins it, right? Because now I don't have a common factor of cotangent in the bottom. It's part of a term. So they will not divide out. So now maybe we're like, okay, so it's not very useful in that format. Yes, this is where the PIDs come in. You know that you can write cotangent squared in terms of cosecant squared. In fact, cotangent squared of beta plus 1 is, in fact, cosecant squared of beta. And now the 1 is gone, so now we can divide out one of the cosecants, yes? And that leaves a cotangent of beta in the top and still one cosecant in the bottom. Now, it's already looking pretty handsome if I do say so myself. But is that a single power or a single trig function? No. So how am I going to know if that simplifies down to anything? Very good. You have the right idea. When in doubt, whether something simplifies down or not, put it in terms of cosine and sine. That's kind of like your ultimate get unstuck strategy. Write everything in terms of sine and cosine. So we're going to finish this one. Cotangent is cosine of beta over sine of beta. And then divided by cosecant, which is 1 over sine of beta. And now state change flip, which I already mentioned I do want to see it. Stay, change, flip. That's sine of beta over 1. And now what happens with your sine of betas? They divide out, and we are left with cosine over 1, which is just cosine. And there you go. That entire thing in the beginning is just cosine in disguise. The most elaborate disguise we've seen today. Yes, Tyler? What do you mean one fell swoop? If you put the negatives together and just went to the third line? Oh, that's fine. Yeah. All right. Memorize the identities if you don't have them. We'll see you back here tomorrow.